In this video, we'll learn about polar functions. So the idea of a polar function is that your input is going to be an angle, and your output is going to be the corresponding radius. So just like a rectangular function would take x as the input and give y as the output, same idea, just take an angle as input, and this time we'll give a radius as an output. So let's go ahead and do a little bit of practice at converting back and forth between rectangular and polar equations. And in the next section, we'll take a look closer at how to actually graph some of these polar functions. So the tools we're going to use pretty much, if I'm going to convert from rectangular to polar form, I'm going to use the fact that x is r cosine theta and y is r sine theta, those same equations that we saw earlier. So for example, with this guy, y equals x squared. For y, I'm going to put r sine theta, and for x, I'm going to put r cosine theta, but since it's x squared, I'm going to square that. So let's work on solving this. I'm just going to square that. So I have r sine theta equals r squared cosine theta. Now remember, polar form equations are always solved for r, so I need to solve for r in this equation. Let's divide both sides by r. And then let's divide both sides by cosine squared theta. So I could leave it here, but it's probably nicer if I simplify this a bit more. So I'm going to rewrite this as sine over cosine times 1 over cosine. Or in other words, I could write this as tangent theta times secant theta. Okay, so that's our first example of converting a rectangular equation into polar form. And again, just as a reminder, in the next section we'll get more experience on what it looks like to actually graph a polar function. For now, we're just working on going back and forth. What tends to be more difficult is converting a polar equation, so that's something that's already in the form r equals something, and rewrite that instead in rectangular form. So we're going to try a few examples of that now. And these are using the same equations that we used earlier. So when we talked about these four guys up here, they're the same ones we're going to be using now. So let's try this first one. We're supposed to solve r equals 2. See if we can rewrite that in rectangular form. So the only equation I know that's going to take advantage of r effectively is the one where r squared equals x squared plus y squared. Okay, so I currently have r equals 2. Okay, so that means r squared equals 4. But r squared can be rewritten as x squared plus y squared. And now I almost have the standard form equation for a conic. Let's divide everything by 4. So you could think of this as an ellipse centered at 0, 0 with a major and minor axis both of length 2, or you could just think of this as a circle of radius 2 centered at the origin. Okay, so even though we haven't really figured out how to graph polar functions, I know from converting this to rectangular, it's a circle of radius 2 centered at the origin. Okay, so there's our first example. B looks a little bit strange, right? We don't have it solved for r. So think about how we normally think about rectangular functions, something like y equals, and then a function in terms of x. But also, sometimes for rectangular functions, you might have like a vertical line, say x equals 2. This is something like that, using that input parameter. So this is saying all the inputs are just equal to pi over 3. Let's see what we could do to convert that to rectangular. So I'm going to take advantage of what I know about theta and how that relates to y and x. So if theta equals pi over 3, let's take the tangent of both sides. Okay, and that's because the tangent of theta equals y over x. So let's see, what is pi over 3? Or sorry, tangent of pi over 3? That is root 3. We can get that from the unit circle. So multiplying both sides by x, y equals the square root of 3 times x. So it's just a linear function, a straight line going through the origin, something like that. Okay, also if you think about it, this represents all the points where theta is equal to pi over 3. So if I did all the positive radii at pi over 3, that would be that side. All the negative radii would be that side. Yeah, it does form that line, so that kind of makes sense. Okay, so let's try another one. Okay, in this third one, we have r equals secant theta. So what I'm going to do for this one, I'm just going to use the definition for secant theta, which is 1 over cosine theta. And now that I'm seeing a trig function that shows up in one of my formulas, let's see, cosine theta equals x over r. So if I simplify that, this is r equals r over x. Well, let's see, what can I do with that? Let's multiply both sides by x, and then divide both sides by r. Oh, well apparently this is just a vertical line all the points where x equals 1. Alright, and then our last one is probably the trickiest one we've seen so far. R equals 6 sine theta. Okay, so we need to think about what we can do to take advantage of the formulas we've learned. Well, I see a sine theta, so I'm thinking, why don't I plug in what we know about sine theta? Sine theta is y over r. So let's multiply both sides by r. But remember, anytime I see r squared, I'm immediately thinking r squared equals x squared plus y squared. Now at this point, this is a non-standard form equation for a conic. I just need to think, what kind of conic is this, and how can I get it into standard form? So go ahead and pause the video, see if you can get this guy in standard form, and decide what it is. So let's see, I'm going to go ahead and put these y terms together. And then I need to do completing the square. I'm adding 9 to both sides here. That's because negative 6 divided by 2 is negative 3. Negative 3 squared is 9. Okay, and now that I have that, I very nearly have it solved for 1, so let's divide everything by 9. Now it's in standard form, or if you prefer, you can even rewrite these 9s as 3 squared. So there it is, this is another circle. This time it's a circle of radius 3, centered at 0, 3. Let's do a quick sketch of what that would look like. So it's centered right here. There's that circle. Okay, so that's what that equation is. We've just rewritten it as a conic in standard form.